and we will begin what the electrostatic potential energy is first. Before I define the electric potential, I will define another subject which is directly related to the energy. So think a charge which is located in some point in space, charge Q. And if you want to bring a second charge which is near this charge Q, do you have to do some work? Imagine there is a charge at infinity, it's a large distance, and you bring this second plus charge to some position which has a distance r to the original charge. Suppose you do on a line, okay? You bring this Q initially located at a very far distance, and you bring on a line toward this plus Q, large Q, to a distance r. Do you have to do a work to do this, to bring this charge? Why?
Because there is a force that repulses.
Exactly. Yes, because there is always an electrostatic repulsion force between like charges, and what you do here, you bring another plus charge from a very far distance to a point. When you come closer and closer, you will feel a force, it's a repelling force, right? Because it's the same charge, and you bring two charges close to each other, you will feel an electrostatic repulsion force. And you go against this force, so you have to do work, right? And as you have seen in previous semester, that the work is defined as, what is the definition of the work? If you apply a force, okay, to an object, and you move that object with that constant force a distance r, well, let's say a distance x, the work you have done is F times x, right? The force times the distance. Because in all over the motion, you're applying the same force, F, and you move the object a distance, a position x. So, in fact, this is an integral, right? If you have a variable force, if the force is changing, okay, then you can again define the work, but the work, definition of the work this time will be an integral. And so, when you bring this charge from infinity, there is this red force, the electrostatic repulsion force, but the force applied by you or by me against that force. I have to overcome this force. At least I have to provide the same strength of force to move the charge, right, near to this point. So let's write down the work done by me, okay, to move this charge from infinity to a position r, which is the distance between this steady charge and the charge you move. Well, this is just the definition of the work, and you have to provide this work, this F dot dr, the line integral. You multiply the line vector. If you move along this line, right? If you move along this line, then dr is a small length which is in this direction of the motion. And if this is an x-axis, dr is nothing but dx, right? Why I have to write down this as an integral? Because the force is changing. The force is changing all during this motion. And so if the force were constant, then I will just multiply this constant force times the total distance from infinity to there. But the force is not constant, so I have to write down this integral. But don't worry about it. So we can always take the integral easily. So instead of writing inside this integral the force applied by you, I can replace this force by the electrostatic force between these two charges, right? Because the electrostatic force is just the same strength but in the opposite direction. So let's do this. I replace the F, the force provided by me, by the electrostatic force between these two charges. Okay? Anywhere during this motion, I can always write down this electrostatic force. As long as I know the distance between the charges, the electrostatic force is just equal to K times capital Q, the initial charge, the small q, divided by distance squared. That's it. But since the directions are reversed, if me is equal to minus F electric force, instead of writing minus in here, I just change the limits of the integration, the order of the limits of the integration. Because whenever you change the order of the integration limits, there is a minus sign in front of the, right? That's it. So now I express this work done by me to bring a charge from infinity to this point, which has a distance r to the original charge, as this kind of integral. So as I can always write down this expression explicitly. Let me write it. It's just q times small q times large q divided by 4 pi epsilon 0, or you can replace by k. K, small q, large q, divided by r square, but r square will be inside integral because the integration variable is r. So the integration limits are there from r to infinity, and 1 over r square integral is easy. What is the integration of 1 over r square? Is 1 over minus 1 over r, and you can find this result as small q times the second charge plus large q, k divided by r. This is the total work or the energy provided by you to bring a charge from infinity to a place which has a distance r to charge plus q, capital Q. Okay, this is the work. The work is equal to energy. Work, what you do work, is nothing but an energy, right? And this expression, in general, if you bring two charges from infinity to a position where the distance between these two charges is equal to r, you have to consume an energy which is given by this expression. Okay? The multiplication of two charges, q1 and q2, times k, divided by the distance, final distance in the final configuration. Okay? If you keep the distance r from infinity to r, then this is the amount of work you have to consume. This is called the electrostatic potential energy of 2-point charges, q1 and q2, which are located at a distance r from each other. Okay, this is the definition, and we all base the concept of electric potential onto this electrostatic potential energy. So, well, this is potential energy, but what is electrostatic potential? Electrostatic potential is not the same with potential energy. Electrostatic potential is not the same with electrostatic potential energy. It's something else. Now I will make a difference. Suppose, again, you bring this small charge q from infinity to this point, and you have to consume this much amount of energy, right? If you bring not the plus small q, but plus 1 coulomb, the unit charge, from infinity to this position, with the existence of this capital charge q, what is the amount of electrostatic energy? It is just this u divided by q, because instead of q I use 1, just 1 coulomb. And this is the definition of electrostatic potential by this charge q at a point P, which is located a distance of r away from it. The potential, electrostatic potential of this charge q at this point P can be expressed in terms of the charge and the distance between these points. That's it. It is q divided by k times q divided by r. Okay? So in this expression, as you see, do not contain a second charge. The electrostatic potential is not equal to electrostatic potential energy, and the electrostatic potential for a point charge at a point P, which is R away from it, is equal to this expression. Okay? So the electrostatic potential can be positive if you have a positive charge, and it can be negative if you have a negative charge. Okay? And of course, you can have a zero potential everywhere if you have no charges at all. So I hope this is understood clear. There are two concepts in here. One is electrostatic potential energy. It requires at least two charges, okay? And the other is electrostatic potential. It only contains one charge only, okay? And the electrostatic potential for one charge is defined by this equation. It does not have a unit of energy. And the unit of energy is just joules per coulomb, because I divide energy by the charge to get this expression. And this has a special name. It is called volt. Okay? The volt is 1 joules per coulomb, 1 joules divided by 1 coulomb, and it is the unit for the potential, electrostatic potential, in the SI unit system. Okay. So with this expression, then the electrostatic potential of a point at infinity, at a very, very far distance, by definition is zero, right? Even if you have charge located near you, in some region of space, as long as you consider a point at infinity or very, very far away, that potential of that infinity, potential of a point at the infinity, is defined as zero potential. So I make this very clear. Whether you have charges here or not, the potential of a point at infinity is always, always zero. Okay? All right. What if you have more than one charge? Suppose you have one charge here, and the other charge at some other place, and you want to find the potential of a point P, which is close to these charges, okay? If you know the distances of each charge, right, to this point P, and the potential, electrostatic potential of that point is just the addition of each potential of each charges at point P, right? So you can add the potential by just adding like scalars. First of all, the potential, electrostatic potential, is not a vector like electric field. It is a scalar, and you can always add scalar without worrying about the direction. Okay? You don't worry about the direction. The potential of a point P, which is located at some distance to some charges, point charges, all you have to know is what is the distance between the point and these charges. You just write down the potential of each charge at point P, right? And add them. That's it. So the result is the addition of all potentials of each point charges at point P. So as you see, the potential, even if you have charges around at this point P, might be zero, right? If the totality of all charges is, net charges is zero, and if these distances are equivalent, then at this point you will have a zero potential. This is possible. Even you might have a negative potential at this point, or you might have a positive. So potential can be a negative quantity, can be zero, or a positive quantity. All right. So the next question is, suppose you don't have a charge in one region of space, right? But instead you have electric field, a non-zero electric field, right? And you put a coordinate system, and you want to find the potential of any point P, which is located r distance away from the origin of this coordinate system. Suppose you have no charges You just have one region of space which has a non-zero electric field. Okay? So in this region, even if you don't have any charge, can you talk about the potential of a point? Yes, this potential of point P, which is located inside a region of space which has non-zero electric field, is defined by this integral. Okay? The integral is from point R to the infinity, the electric field E dot dr. So you can ask, what is this dr will be taken from? And in which direction I will go to the infinity? In every direction, any direction is okay. You can go to the infinity on a line, or you can go to the infinity on a curved line, on a curve, on different lines. Doesn't depend on the line you choose. It doesn't depend on the path you choose. This integral is always the same. You will see this. Okay, I will show this to you in an example. Don't worry about it. There is no difference. But if you take this integral in different paths, of course, dr will be different for each path. So only difference is you have to work for different drs. Right? I will explain, I will clarify everything in examples. Alright, so the next is, what about having 2 points in a region of space, let's call these A and B, and you want to find the potential difference between these 2 points. Because, as I said, you can define a unique potential for every point, P. If every point has some potential, unique potential P, then any 2 points will have some different potential. And the question is, what is the difference of the potential of these 2 points? So the potential difference is very important in physics, as you will realize as time goes by. You will see that the potential difference is very important. And now, since you know what the potential of a unique point, you can easily calculate the potential difference between 2 points which are located in a region of space which has non-zero electric field. And this is given by this expression. Now you don't worry about the infinities. Okay? Don't worry about the infinities. Because initially we were defining the potential of a point with respect to a point which is at infinity. Okay? But the potential difference do not require any point at infinity. Just 2 points is enough. Well, the potential difference between the point B and A is just VB minus VA, and it is usually called delta V. I will symbolize this later as delta V. It is equal to minus of the integral, and the lower limit of the integral is the last point A, and the upper limit is the initial point B, because you are going from point B to A. If you are talking about VB minus VA, that means your initial origin of the motion is B, and the final point is A. If you are talking about the potential difference VA minus VB, then you are going from A to B. Okay? Alright, so it is just equal to this electric field line integral, electric field dot dr. So what is this dr? Again, there are many ways to go from, the initial point is A. From A to B in any way, in infinitely many different ways. You can go on a straight line. You can go on a curved line like this. You can go another curved line like this. You can go infinitely many ways, different ways, from point A to B. But the thing is, the potential difference do not depend on the path you choose. It only depends on the endpoints. You will also see this in an example that I will show now. Okay? So this is the definition of potential difference between 2 points, and it's just expressed by this line integral. Alright. It is independent of the path. Let's do an example. Suppose you have this electric field which is constant everywhere, and it's downward in the coordinate system that I put here. the up is increasing y, and the electric field is down, it is in the negative y direction. And you choose 3 points, A, B, and C. Let's imagine these 3 points are on the corner of a right triangle. Okay? Arkadaşlar biraz sessiz olun. And the first question is, well, you can always express the quantities, the distances between A, B, and C. And the distance between A and B is D. And distance between B and C can be expressed by this angle and D and R. And the distance between A and C is R. And these two sides are perpendicular to each other. Okay? And the first question is, what is the potential difference between B and A?
The minus integral from A to B.
Okay, let's first express, write down this most general expression, okay? And we will apply the quantities in question. So the potential difference between B and A is just this integral, okay? E dot dr. So how do you go from A to B? If you are talking about VB minus VA, then you are going from A to B, okay? You are going from A to B. If you are talking about VA minus VB, you are going from B to A. Okay? This is the convention. So, the simplest way to go from A to B is just this line, right? You just go along a line, along a line, which is parallel to the electric field. If you are going on a line which is parallel to the electric field, then this dot product is constant, right? And dr, since you are going from A to B in the y direction, in the y-axis, dr will be dy, right? Because you are going in the y-axis, on the y-axis, the infinitesimal distance element on the y-axis is just dy. All right. And E is constant everywhere, okay? E dot dr is just E dot dr because they are parallel to each other, and the angle between them is 0. Cosine, because E dot product with some another vector A, let's call dr, is E times dr times cosine of the angle between them. But since they are parallel, the cosine of the angle is 1 because cosine 0 is 1. So the result of the integration, since E is constant all the way, E is not changing, E is constant, you can take the E outside the integral because it's constant. And inside the integral we have dr. If you take dr from one point to another point, then this is just the total length from point A to B, right? And the total length is nothing but from A to B is D, right? So the result is minus E times D. Again, E is constant. I have given this E electric field vector everywhere constant in this downward direction. So you see the result is negative. That means the potential of point A is larger than the potential of point B because I'm taking the difference VB minus VA, right? If this is a negative quantity, then that means the potential of A is larger than the potential of B. Think going down on the surface of Earth. Higher places have larger potential energy, and lower places have lower potential energy, because the force is always downward, right? Just like in this example, the electric field is downward, and the electric field plays the role of a gravitational field, which is downward, and you are going from a higher point to a lower point. The lower point has always a lower potential, and if you take the difference of the lower potential to the higher potential, it's always negative. This is expected.
B minus is minus.
VB minus VA.
No, B minus it's minus.
This is?
Yes.
Well, this E is plus. This is the magnitude of the electric field. It is not minus. Okay?
You calculate integral from F to B. will be B minus A, right?
When you calculate from A to B, it's a plus integral. But since you have an extra minus sign in here, okay, this extra minus sign gives the result minus. And this E is always positive because it's the magnitude of the electric field. Let me write down more explicitly here. Well, this will be better. The E is equal to minus some positive quantity E0 J. Okay, J is the unit vector, and E0 is always a positive quantity. And if you take dr vector as minus dy times j. If you put everything in here, into the integral, you will see that this is the result. And you will have, of course, E0 in here, but the result is E0 times d negative. Minus, we have minus sign in here. E0 times d is always positive, but since you have an extra minus sign in here, the result will be negative. Okay? I didn't do it explicitly by putting the coordinate system, but you can do. Alright, let's talk about another potential difference, the difference between C and A this time. The potential difference between C and A, okay, VC minus VA, is going in this electric field, is going from A to C. Alright, let's write down this integral. The definition is minus this integral from A to C E dot dr. Well, this time, again, to make it simple, you just go from A to C on a line which is in the direction of this r vector. And this integral, if E is constant, and also if r is constant, is nothing but just the electric field E dot the position vector r. Okay? And what is the result? The result is you multiply two vectors, dot product, the magnitude of the first vector, the magnitude of the second vector, times the cosine of the angle between them, right? And this angle is this here, because the electric field is downward, and this is the r vector, so the angle between them is just theta. So this minus comes from the definition of the integral, and E times r times cosine theta. But look at carefully here. What is r times cosine theta in this right triangle? In this yellow triangle, r times cosine theta is nothing but d. So it has the same difference with the previous one. Okay? You have the potential difference between point C and A, and between point B and A is the same. That means the potential of point B and the potential of point C is the same. Right? The potential of point B and the potential of point C is the same. That means VB minus VC is equal to 0. Let's check this. Let's check this by using the integral again. The potential difference between C and B, VC minus VB. So write down this again integral, the same integral. The limits of the integration is B and C. E dot dr. If you go from B to C on this line is perpendicular to the electric field, right? That means at every point on this line, E dot dr is equal to 0. So you have zero potential difference between B and C. Okay. We have a spherical shell of charge Q, and the charges are all distributed over the surface of the shell evenly. It has a radius of capital R, and the question is, what is the potential inside and outside of this spherical shell? So we will start by picking up a point on the outside of the shell, and let's call this point P, and let's have this distance from the point P to the center of the shell as small r, and the definition of the potential at this point P is given by this line integral, as we have discussed in the lectures. And this line integral from the point P to infinity of the electric field created by this shell. So we know that the electric field created outside of a shell is just the electric field of a point charge of Q, and we put this expression for the electric field dot product with dr. Well, we will take this line integral over this line starting from point P on a straight line going to the infinity on this line that crosses from the center of the sphere. So it's easy because we have KQ, they are constants and can be taken outside the integrals. We have dr over r square inside the integral, and 1 over r square integral is just minus 1 over r, and minus 1 over r and evaluated at infinity and r is just 1 over r. So KQ divided by r, where r is the distance of the point P to the center, and if the point P is outside the shell, this is the potential of that point. Next, we will take a point inside the shell, okay, and again let's call the distance to the center as small r, but this time r is less than the capital R, which is the radius of the shell. So again we will use the same definition. We will calculate the potential by using the line integral of the electric field from this point R to the infinity. But we have to break this integral into two terms, because when you go on this line starting from point P inside to the far distance, you crosses this special border of the shell at r is equal to capital R. So we break the integral into two parts. When first take the integral from R to the capital R, okay, which is the radius of the shell, plus from this capital R to the infinity. So we have two terms now. Why do we have to break up the integral into two pieces? Because the electric field is not the same everywhere. For the points inside the shell, we know, we already calculated this by using the Gauss law, the electric field inside a charged shell is equal to 0. So the contribution from the first term, first integral, will be 0, because from R to capital R, the electric field inside the shell is 0. So we are only left with the second integral, and this integral is again easy, just like this one. It can be taken very easily. It is just k times, or 1 over 4 pi epsilon 0, q divided by the capital R. So this is true for every point inside the shell. For every point inside the shell, the potential is just this term, is kq divided by capital R, because the electric field is equal to 0 wherever you go inside this shell. If you have a charge in your pocket, wherever you go inside the shell, you will not experience any force. If you don't experience any force, that means you don't change the potential, and the potential just the same as the potential of any point on just the surface. Okay. So this is the graph of the potential for all points inside and outside the shell. So from r is equal to 0 to the capital R, where this is the radius of the shell, the potential is just constant. It is a constant value of this kq divided by R, and right from outside it drops as 1 over R to the infinity. So at infinity the potential is again 0. You can easily check, because for all points located at the infinity, the potential is always 0. So you can check this from this expression. let's picture the problem. So we have two concentric cylinders, and the inner cylinder is a metal rod which has a radius A, and the outer cylinder is a shell which has a radius B, and between these two cylinders we have an empty space. So the inner cylinder has a charge density plus lambda, and the outer has a minus charge density minus lambda. They have the same charge per length in the in this direction. So to calculate the electric field, we separate this problem into three regions. The first region is the inner region of the metal rod, but since we know that inside each metal, every metal, electric field is 0, so you don't need to calculate the electric field. It's right away just E is equal to 0 inside when R is less than A. And for R between A and B, we pick a point which has a distance R to the center of the axis of the cylinders, and we choose a imaginary Gaussian surface. Because of the cylindrical symmetry of the problem, this Gaussian surface will be a cylinder. Let's take it as a height h, and of course the radius is r, because this is the distance of the point that we want to calculate the electric field to the central axis. So what we do is, first, of course, we calculate the electric flux through the side surface of the inner of the S1 surface, this Gaussian surface cylinder. But the thing is, the area vector in every point on this side surface is perpendicular to the surface, and because of the symmetry, the electric field will be in the same direction because we have a positive charge inside. So the flux is this closed integral through the surface S1, and we don't even think about the top surface and the bottom surface of the cylinder, because the electric field and the area vectors are perpendicular to each other in these top and bottom surfaces, so they contribute a zero flux. So the only flux contributed is coming from the side area of the cylinder, and it is just the strength of the electric field times the side area of the cylinder, which is 2 pi r times h. And by the Gauss's law, this flux must be equal to the charge inside divided by epsilon 0, but since the height of the cylinder is h, the amount of charge which resides inside this Gaussian surface is just h times lambda. So this is the total charge inside, and from this we can easily solve for E, and E will be lambda divided by 2 epsilon 0 times R. So that means in the region between these two cylinders, the electric field will decay as 1 over R as you go away from the central axis. So this is the expression in between. The next question is, what is the electric field when you pick up a point which is outside the spherical shell? So that means the radius will be larger than B, because B is the radius of the outer shell. And again, we follow the same schedule, that we choose a Gaussian surface, which is a cylinder that passes through the cylinder, that passes through the point that we calculate the electric field, and everything is the same, and the flux is the same with that one, E times 2 pi r h. But when you come to the charge which resides inside this blue Gaussian surface, it will be, of course, 0, because we have plus lambda charge distribution in the inner core and minus lambda in the outer shell. So if you add them, you will have a 0 net charge. That means the electric field outside these cylindrical shells, the cylindrical metals, conductors, will be equal to 0. So The next question is, what is the electric potential at all points? Well, the electric potential at right on the surface of the outer shell, we claim that it is equal to 0, because the potential at infinity is 0 by definition, and since there is no electric field outside, then if you bring a charge from infinity to the surface of the outer shell, there is no electric field, so the electric field line integral will be 0. Then we will have the same potential, we must have the same potential at that of infinity at the surface of the outer shell. So this is the reasoning that we should have the potential of the outer shell is equal to 0. And next, let's choose a point in between these two cylinders, and the R is in between A and B. So what is the potential of that point which is inside in between the cylinders? Let's take this point as a distance R to the center, and well, since we always define the potential difference, well, let's choose a potential, a point which we know the potential. Let's choose the potential difference between this point VR and the potential of the outer shell VB. Since we know the potential of VB, it's just a 0, and the definition goes like the potential between any 2 points is nothing but the minus of the line integral between these 2 points, line integral of the electric field. So we put R in the upper limit and the B in the lower limit. And the thing is, we know what the electric field inside. We know what the electric field in between these two cylinders. We already have calculated from the Gauss's law. So next is just put VB is equal to 0 because of the reasoning that we previously considered. And then the next thing is just replace, interchange these limits, put B to top and R to bottom, and then changes the sign of the integral. And inside we have E dot R. From E dot R we have 1 over R integral dr over R, and it is very easy to take because 1 over R integral is just logarithm, natural logarithm. And if you put the limits of the integration, we will have the final expression lambda divided by 2 epsilon 0, 2 pi epsilon 0 times the natural logarithm in parentheses B divided by R, where R is the point in between these two cylindrical shells. And of course the rest is what is the potential of any point on the surface of this inner cylinder, metal cylinder. Just put R is equal to A in here, and then the potential will be all the same through the volume of the inner cylinder, because there is no electric field. The electric field is 0, so whatever the potential we have at the surface, we will have the same potential in the inner region. The charge rod is on the x-axis and extends from x is equal to minus a to the x is equal to plus a, which is a length of 2a, and the total charge is q. So the question is, what is the potential of a point which is located on the x-axis, a distance b from the origin or from the center of the charge rod. So what we do is, since this is an extended object, it is not a point charge, we divide the rod into small charged pieces which we call dq, and we express the potential of all these dq charges at point P and then add them as an integral. So let's pick up any piece which is away from the center or the origin, charged dq, and express the potential of this dq at point P. So if the distance from the origin is x, and if the distance of the point from the origin is b, then the distance from the charge dq to point P is b minus q, and by the general expression of a point charge as kq divided by r, we express this infinitesimal potential created by dq as k times dq divided by b minus x. So next is we express this dq charge in terms of the charge density and dx. We have this expression dx because it's a line charge, and if we multiply this dx, the infinitesimal length in the x direction, by the charge density, we will get dq. So we express also the total line charge density in terms of the total charge and the total length of the rod as q divided by 2a, and finally we express the total potential by integrating the dV expression from x is equal to minus a to x is equal to plus a, because the charge extends from minus a to plus a. And we have inside the integral dx divided b minus x, and the integral of this quantity is just the natural logarithm minus ln b minus x. So the result is, after putting all the integration limits, we get k times q divided by 2a ln b plus a divided by b minus a. So the next question is, if we release an electron on the x-axis at x is equal to 3a from rest, what is its speed at x is equal to a? To solve this, it is enough to express the potential energy difference between these two endpoints for the electron, and we will equate this potential difference to the kinetic energy of the electron by the conservation of energy to find its final speed. So this is the energy equation, and then the conservation of energy requires the kinetic energy of the electron at x is equal to a should be the potential energy difference between these 2 points, and the potential energy difference may be expressed in general by the multiplication of the charge of a point object times its change in the potential, electric potential. We already expressed the potential at any point on the x-axis, so we will utilize this expression for these points x is equal to 3a and x is equal to a. We simply we will put b is equal to 3a as the initial point potential, and put b is equal to a as the final potential of the charge electron, and let's express the potential energy difference as, since the charge of the electron is minus e and the endpoints are Va minus V3a, because x is equal to a is the final point of the electron, and it will be attracted by the rod. And when we express this explicitly in terms of this potential expression and in terms of the charge density, it is the change in the potential energy is equal to k times lambda times e, the logarithm 3 divided by 2. So this will be equal to the kinetic energy, and by solving for v, we will get the expression for the final speed of the electron as in square root 2k lambda e divided by the mass of the electron times natural logarithm 3 divided by 2. So in this problem we have again a charged rod, and it is placed on the x-axis extending from x is equal to minus a to plus a, and it has the total charge q, so the charge density is just q divided by 2a. This time the question is, what is the potential of any point which lies on the y-axis? and it has a distance b to the center or the origin of the coordinate system. And what we do again, of course, we divide this charged rod into small pieces which we call dq, because each piece has a charge dq, and express the potential of these dqs on this point. And let's choose a dq which is away from the origin at a distance x, and the distance of dq to the point in interest is called r, and dq may be expressed again in terms of the line charge density times dx, and this forms a right triangle x, b, and r, and so that means we can express r in terms of b and x by the geometry. R is the hypotenuse of this right triangle, and it is in square root b squared plus x squared. So we express the infinitesimal potential created by the infinitesimal charge dq at this point as k times dq divided by r, and if we write down all the terms explicitly in terms of the variable x, we get k lambda dx divided by x squared plus b squared in square root. Next, we should integrate to find the total potential from x is equal to minus a to plus a, and the integration of this quantity can be found from the integration tables, or it can be integrated by using the change of variables. So simply it is the logarithm x plus in squared x plus b squared, x squared plus b squared, and we evaluated at the endpoints of the integration. So the final result is the potential at any point which lies on the y-axis, a distance b away from the center of the rod, is expressed as k times lambda times the natural logarithm a plus in squared h squared plus b squared divided by minus a plus in squared h squared plus b squared. So again, we have the question of if we release an electron on the y-axis from y is equal to in square root 15a, the question is what is the speed of this electron at y is equal to square root 3a. So again, the change in the potential energy of the electron will be equal to the kinetic energy gained by the electron, because it is released from rest. So the final speed may be expressed in terms of the potential energy, and the potential energy is just the charge q in general times the potential difference, and we have already obtained the potential of any point on the y-axis. So instead of q we will replace minus e, and if we put the final points, also the difference of the potential at the final points, we express this change in the potential energy as the electron charge times the Coulomb constant k times lambda the charge density times the natural logarithm 5 divided by 9, and this will be equal to the speed in terms of as we put everything in this energy equation in square root 2k lambda e divided by the mass of the electron times the natural logarithm 5 divided by 9. We have a charged ring, and the charge is distributed over the ring evenly, and it lies on the YZ plane, and the x-axis is the symmetry axis of the ring, and passes through the center of the ring. The question is, what is the potential of any point which lies on the x-axis having a distance x to the center of the ring? So the ring has a radius a, and we will start by dividing the ring into small charges, small pieces of dq, and these pieces are little arcs of the ring. So let's choose an dq charge on the rim of the ring, and the distance from this to the point in question, let's call this r. And if you look at carefully, this side, which is the radius of a, pointing toward this charge dq, and the distance x is perpendicular, and this r is the hypotenuse of this right triangle. So r can be expressed in terms of a and x. Then we can easily express the potential of this charge dq at the point P. So it's just k times dq divided by r. And we can express r in terms of, as I said, a and x. R is equal to the square root of a square plus x square from the hypotenuse theorem. And if you write down this integral to find the total potential, because we add all dq's over the rim of the ring, and we see that we can take this distance r easily outside the integral because it does not depend on any variable. Both a and x are fixed, they don't change. When you run this dq all over the ring, this distance r does not change. So we can take r outside the integral, and we are left with the integral of dq, but the integral of dq is nothing but the total charge on the ring. So the result is k times the total charge. We have a charged disk which has the total charge q, and the x-axis is the symmetry axis of the disk, and the question is, what is the potential of any point which lies on the x-axis, which is the distance x to the center of the disk. So we can think of the disk composed of rings of radii running from 0 to small a. The small a is the radius of the disk. So, and we know for each ring of having thickness dr, the expression for the potential, and once we get this potential expression for all the rings, we having radii running from 0 to a, which has thickness dr, then we can integrate to find the total potential. So before that, let's express the surface charge density of the disk as the total charge divided by the surface area pi a square, and our dq's will be the total charge on these rings having radius r. Okay, so we will express this total charge dq on this ring in terms of the distances and the surface charge density. So this dq is the total charge of the ring, but the ring covers some area on the disk because it has a finite distance dr, a small distance, and to find the total charge on the ring, what we do is we multiply the surface charge density by the area covered by this ring. But the area covered by this ring is this expression, the total length of the ring, which is 2 pi r if the ring has a radius r, times dr, and dr is the thickness of the ring. So once we fix this expression for dq, now we are ready to write down the potential of each ring as dv. Okay, so and let me show it as k times dq divided by the distance of the ring, every point of the ring to the point in question that we have to calculate the potential. So this is fixed. It is in terms of the radius of the ring, r square plus x square in square root. And we can express also the dq explicitly in terms of r and dr. So this is the expression for the potential of all these rings, and to find the total potential, then we have to integrate this dv from r changing from 0 to small a, which is the radius of the disk. So let's write this down, and here r is the radius of these rings, and these are changing from 0 to the total radius of the disk. So we got this expression, and we can take the constants outside, and the result is k times 2 pi sigma, and in squared r squared plus x squared is to be evaluated at r is equal to a and 0. And you can replace even k by 1 divided by 4 pi epsilon 0. So the end result is, in terms of the charge density, sigma divided by 2 epsilon 0 in parentheses a square plus x square in square root minus x. Here x is the distance of the point in question to the center of the ring disk, and a is the radius of the disk.